first things you think see that's important? Okay, that's moles of what? To remove moles of electrons. Okay, so 279.7 kilojoules is required. That's energy required to remove 1 mole of electrons from, just in case, from 1 mole of lithium. Okay? What are we looking for? Wavelength. We're looking, so our question is wavelength max, or just wavelength, that can remove an electron. How is that different than what's given? Okay, so it's given 1 mole, we're looking for 1 electron. What's that number that pops in your head if we're thinking between mole and a single one of them? Okay, so we're probably going to have to use Avogadro's number, 6.022 times 10 to the 23rd electrons per 1 mole of electrons. We'll use that at some point in time. Anything else? Well, we're looking for wavelength, and we're given what? Energy. Kilojoules, right? We're given energy. We probably need to do what with the kilojoules? To get to joules, straight joules, so we can use what equation? What's the combined version of speed of light equation and the energy equation? hc over wavelength, but we don't care about energy. We have energy, right? So lambda is equal to hc over E. Okay, so that's probably a good starting point to at least plug our information in. But we have energy in a weird way right now. It's not expressed the way it needs to be expressed. So what I would encourage you to do, I've solved this 2 different ways. I like the second way I solved it better. What is our kind of main point to start with? We know that it's asking for the maximum wavelength light that can remove 1 electron. So I'm going to start with 1 electron to figure out how much energy that is worth. So I can use that form of energy in E because everything else is a constant. So 1 electron. What do you do from there? Noting what we are given. Go to moles of electrons, right? So 1 mole of electron has 6.022 times 10 to the 23rd electrons in it. Okay, so electrons cancel. I'm in moles of electrons. What has to be my next step? Based on what's given. It's all based on what's given.
1 mole.
Right. 1 mole of electrons has 279.7 kilojoules of energy in it. There you go. So once you get started, you don't stop it. Like, you know how to do stoichiometry. 1,000 joules is 1 kilojoule. And that gets us energy. That energy we can plug into energy and solve for wavelength. That's a little hard to read and figure out, so I wanted to lead you on that one. But they can give you funky givens, but you can manipulate it to the place that you need. When you calculate energy, that is 4.64 times 10 to the negative 19 joules. What do you notice for wavelengths of light? The energy generally is about. You may have calculated this 4 times in your life. Usually 10 to the negative 19th is where our energy lies. And then where does our wavelength lie? Which is what's what?
400 centimeters.
So 400 nanometers, 700 nanometers, which is 10 to the negative 7th meters. Okay, that's how you kind of know you're in the right area if you are trying to calculate. So this energy goes into energy here, and then you guys can do the rest there, okay? And here, calculate it real fast, and then we'll jump into quantum. I'm expecting you will memorize your H and your C value, okay? So when you plug in the H value, the C value, and that energy, what do you get? Say it again. 4.28 times 10 to the negative 7 meters. How many nanometers is that? Do not calculate how many nanometers is this. I'm going to go 428 nanometers. What color of light is that? Close to. Probably violet. You see, you know all this stuff. If you practice it enough, it becomes a little easier. but you can make a lot of assumptions up front if you know some of your background knowledge, and that's our key here is speed on this stuff, okay? Okay, quantum. Quantum numbers, you read some about here. The quantum numbers are simply an address of where the electron exists. And I have some notes, some previous notes on it first. I'll see exactly what I want to do based on your level of knowledge. How about do me a favor, circle 52B. I highlighted the ones I want you to do. 52B on your little homework section. And 40. So 52B and 40. That's what I know for sure. Those two questions I need you to do. Okay. Quantum. I'll come back to this model. Please, yeah. What's a mega? Oh, okay. So I'll take this up tomorrow from you guys. I want to finish quantum. King Henry died by drinking chocolate milk, micro, nano, pico, mega. Mega's 10 to the 6 from base. Know that. Okay, quantum numbers. The 4 quantum numbers are called different things. Principal quantum number can be related to its energy level. It's also called the N number. Well, where have we seen N now before? Yes, that is true. That's in electrochem. Give me an atomic structure. Where does N come up? Energy level from the Bohr model. So we're using Bohr. We piggybacked off Bohr. Now a bunch of scientists came together to make up the quantum mechanical model, which is our modern model. And we'd like to know a lot more about where the electron exists in the atom. Mainly more about its where it is, how far away from the nucleus it is, how does it spin. That's mainly what we're talking about right now. So the 4 quantum numbers are, the first one is our energy level. The second one regards the shape of the orbital. So this is kind of like our outline, and then we're going to get into the actual numbers in just a minute. The principal quantum number can be expressed as 1, 2, 3, 4, 5, 6, 7. But we usually call that n equals 1, n equals 2, and so forth. The orbital, which is like the angular momentum, it has a funky name, angular momentum quantum number. It's going to be regarding the shape of the orbital. We know the shapes are spherical, dumbbell, double dumbbell, and flower. They have each of these sublevels have a different number that describes them. So S is described by a 0. P is described by a 1. D is described by a 2, and F is described by a 3. There are theoretically such things as G orbitals, H orbitals, and so forth, but we haven't discovered or have data for them yet, but it's theoretical because it's a trend. So what we've done is we've figured out how far away it is from the electron is away from the nucleus. Which orbital is it in that level? So this is called a level. This is called a sublevel because it's within that level. And these orbitals these sublevels come with many orbitals in them. The terminology is very specific. Okay? The orbitals are within each of the sublevels. So the orbitals in the s orbital, there's only one orbital. It has to be in the s sublevel. Remember, whenever you draw your orbital diagrams, there's a single slat we put them in. And the p orbital, there's one s orbital. Let me rewrite this. One s orbital. How many p orbitals are there? How many lines do you draw for your orbital diagram for p? 3. 3 p orbitals. Okay? And they are given numbers from -1 to 1 to represent them. So this is -1, 0, plus 1. The s orbital that we're talking about, we call it 0 because it's right in the middle of the L numbers. These are I have more details on the next slide for you. I'm giving you the basics right now. So what's next? How many orbitals? How many orbitals are in D? How many slots do you draw for 5? There are 5. Do you see the trend? 1 orbital, 3 orbitals, 5 orbitals for D. And guess what their numbers go from that describe them? Yep, -2, -1, 0, +1, +2. Because these numbers should describe the number of orbitals present. There are 5 of them. And then the F orbitals, how many are there? There are 7 F orbitals. And whenever you draw your your orbital diagrams regarding the electron configuration, you draw 7 little slots for those electrons, and that's related to the 7f orbitals. And they go from -3 to +3. I'm not writing all those out. Okay. So the first quantum number tells us how far away the electron is from the nucleus. The second quantum number tells us which orbital exists in that field. I'm sorry, which sublevel? I keep saying orbital. Which sublevel? The third quantum number tells us of that sublevel which orbital we're looking at. Sometimes there's only 1 to look at, so there's no big deal. Sometimes there's 7 to look at, so we get to pinpoint which of these orbitals we're looking at. The very last quantum number tells us in that orbital there are 2 electrons. One spins up, one spins down. So the spin is our last quantum number to describe the address or the behavior of the electron. Clockwise is given a +1/2 number. Counterclockwise is given a -1/2 number. So when I say quantum numbers, we literally describe the address of an electron with numbers, not words. So each of these words are given a number to describe them. So I could tell you the quantum numbers for an electron, for the last electron in an atom is 2, 1, 1, +1/2. That would be its 4 quantum numbers. That means something to us, though, okay? So these 4 quantum numbers tells us, first, what is this 2 representing? N, which is what? The terms are very specific. Energy level. This is the second energy level. Okay, so on your periodic table, you have the periodic table available. On your periodic table, we're looking at lithium over to neon. That's the second energy level. What did the second quantum number stand for? The shape of the sublevel. What was the 1 designated to be? P. Good. Okay, here's how I remember it. I'll show you this now before I forget. Okay, the values, and these are called the L values. So angular momentum is that second quantum number I just discussed. It represents the sublevel, the shape of it. It depends on the N value, and I'll tell you why in a second. But the numbers are 0, and so it isn't a 0. I always say 0 is a fist because that's a spherical shape, which is S orbital. The P orbital is like that. The D orbital is like that. So 2. This is me being helpful, okay? So S, P, D. 1, 0, 1, 2. And then you can keep going. But as you describe them, you do have to denote a positive or negative eventually. Okay, so you're right. The first, or the L number 1, or the angular momentum number of 1 represents the P sublevel, P-shaped sublevel, and there are 3 of them, which we're going to get to in just a second. But as you go from the S sublevel to the P sublevel to the D to the F, those get higher in energy. So as you get increasing in L number, they get higher in energy. Yeah. Let's come back up to that in a second. That's it for the second quantum number. The third quantum number depends upon the L number or the quantum or the angular momentum number. Oops, I'll come right back to that. Okay, so this is the ones that I was saying goes from a negative to a positive. So what are the possible third quantum numbers, or the magnetic angular momentum quantum numbers? They're going to be for for an s orbital, it's just 0. And like I said, for P, there are 3 orbitals to denote, so they go in 3 different axes: Px, Py, and Pz. What is that? What do you think that helps to show? Yeah, so there's a P orbital that's going on the x-axis, P orbital on the y-axis, and there's P orbital on the z-axis, which gives it that one goes like this, one goes like this, and then one goes into the board and out of the board. So it gives it that 3D shape to the 3 P orbitals. But we, instead of calling them Px, Py, Pz all the time, we call them -1, 0, or positive. Those numbers are giving you which of the axes, but there's not exact. They don't have to be X, Y, and Z. That usually is the conventional way of writing it, but these are all degenerate orbitals. What does the word degenerate mean? What's degenerate mean? Oh, I don't think that's actually not here. They all have same energy. So the px, py, and pz, they all mean, that means they simply just have the same energy. So on a sublevel, S is low energy, all the way up to F is high energy. But within the sublevel, each of those orbitals are at the same energy. And I'll show you a picture of that in just a second too. Oh, I do have it right there. Boom. Okay, so then that's kind of what I'm talking about when I say from -1 to +1. And then the spin is going to be in relation to the response to the magnetic field or the electrical field. So an S is that last quantum number. So I called it just the spin, but S is actually the label for it. And the first one is clockwise, the second one is counterclockwise. They have to spin opposite in an orbital. Do you guys remember drawing it like this? Your orbital orbital diagrams. That means a plus 1/2, and a -1/2. -1/2 spin whenever you draw them like that. Okay. So and I'll go into some more examples, but the whole 3 rules for ordering of your electron configurations: off-balls, Huns, and Pauli. Those 3 rules come from actually the quantum numbers. The Pauli exclusion principle is one where we will always pair up our electrons, but that's kind of our honors chem definition. The AP Chem definition is that every electron has its own personal set, unique set, exclusive quantum numbers. So it's called the Pauli exclusion rule, because no other electron can have your same quantum numbers, your same address, because there's no other electron in your spot in the atom. So we call that an exclusive set of numbers. So I'm going to go back to my example at the very beginning. I see some dead looks with me a little bit. Will examples help?
Yes.
Thank you. Okay. Okay. Where's that example it started with? Oops, right here. Okay. So I said this is the N number. That's the energy level. So we're talking about the second energy level. This is the sublevel. And what shape is this sublevel if it's a 1?
P.
The p orbital. Okay, so or p sublevel. Okay, if I'm talking about another 1 right here, I'm saying positive 1, right? Which p orbital am I referencing? The last one, the z one, right? So that's conventionally how we describe it. We're talking about pz, which is just one of the lobes. And then I'm talking about the final number is going to describe the spin of the electron. So I'm talking about the electron that's spinning up there. If this is the last electron that's put into an atom, which atom is this? It could possibly be, okay, so we're talking about the second energy level. So we're talking about the second energy level, and I'm already at PZ, so that means I've already put an electron in PX, PY, and I'm in PZ. So it could be the third electron in the p orbitals, so it could be nitrogen, or it could be the last one I put in, because I'm not telling you how many electrons are here total. It could be the very last one I put in. It could be neon. Only because I'm not telling you if this last one, if this PZ is the second electron put in or the first electron put in. So let me tell you some more here. Go to this example on page 67. Number 67. Let's talk about the vocabulary a little bit more before we do another example like this, because these are actual 4 quantum numbers describing an electron, but I'll tell you a bit more here too. Okay. So on number 67, you guys have it in front of you because I don't have it pulled up. How many orbitals in an atom can have the designations of 5p? Okay, so I just want you to tell me how many orbitals are in the 5p sublevel. This one's an easy one. No numbers really. P sublevel, 3. Okay, and in the 5p sublevel, we just say there's 3. So this is getting you good with the vocabulary. So the 5p sublevel, there are 3 orbitals. How many orbitals are in the 3dz2? I'll show you what that means. Wrong way. Okay, so what do I mean by this ZD2? The s orbital, there's no orientation difference in the sphere, right? It's all the same. In a p orbital, you got pxy, px, py, and pz. In a d orbital, you have your double dumbbells crossed, right? So we call it y squared, xy, depending on which axis you're lying on, right? Z squared, which has a donut. Okay, don't know how, but it has a donut. And then zx squared, y squared, minus y squared. But if you see any designation like that, it's talking about a single orbital. Because there are 5 different orbitals, different orientated orbitals in the d sublevel. So when it says 3dz2, how many orbitals is it referring to? Just one. It's talking about this, what is it, ZD2? This one? It's talking about that orbital. So when it says 3dz2 or squared, it's saying one orbital. Okay. When it says when it says d4, 4d, how many orbitals are in the d sublevel? 5. Okay, so sometimes they're easier, like what we're doing right now. How about n equals 5? This is the part I've not showed you yet. Okay. Orbitals, they come in the sublevels as based on the sublevel present. Yes. Okay. So here's the last part I'll tell you guys for now, and I'll stop because I think it's almost time to stop. This is something you want to write down right here. This is a trick. If you're trying to figure out just based off one number given to you, for example, the number of orbitals or the energy level that we're referring to, number of orbitals is going to be n squared, so energy level squared, because there are, that's just how it works out. But the electrons, it actually makes sense. Electrons per energy level is 2n squared. And how does that make sense as you come from here to here?
Because there's 2 electrons per.
Right, there's 2 electrons per orbital, like when you draw like this. So that means if that's number of orbitals, you just multiply by 2 to get there. So if we're talking about the n equals 5 orbital, n equals 5, how many orbitals are present? Can be present. 25, because you're saying 5 squared. Okay. And then, how about, I'll hold off on the 67 to 69. So I want you guys to just read into this a little bit more. In the back of your packet, probably fourth or fifth to last page. So right before the labs. It's kind of small because it's an old textbook copy. Older than me. So why don't I number these? I did number at page 40. Page 40. There's more reading on quantum mechanics or quantum numbers. There's some images. This might help you decipher a little bit more. This is in our content. This is in our curriculum very, very, very little. Really, I'm trying to be a good teacher because when you go to college, they expect that you know this. This may not be highly emphasized in our test whatsoever. So I want to expose you to it, but I really want you to get an appreciation for where the electrons are, specifically the quantum numbers in terms of like energy level and SPDF as they relate to electron configurations and orbital diagrams, and the fact that it's our modern model. Okay. So I want you to look into that some more. I'll let you know what homework to do later. But right now, for homework-wise, those are 2 questions I assigned to you, plus your lab. Okay? ASMI tomorrow. When is buffer stuff due? Friday. Buffer test corrections are due Friday. And then come get a cupcake. I'm getting a cupcake for his birthday yesterday. He had his birthday off. And
Birthday was it? Happy birthday.
Jay, come on with his friends. Did you tell anyone?
they're 18. They take one now. Happy birthday to you. Cha cha cha.